Hello, welcome to my presentation about my final project for machine learning for functional genomics. My project is called Using Deep Neural Networks to Predict Mouse Neuronal Connectivity Based on Gene Expression. So the bulk of this project is based off of a paper that was published in 2021, detailing a new technology that was developed by these researchers that was able to get really fine-grained data for a given mouse neuron that gave both its gene expression and also the type of neuronal projections that came with it. So they were able to barcode the neurons in mouse motor and audio cortices, and they're able to find respectively the expression of various genes and also the sort of neuronal connectivity that corresponded to. And the neuronal connectivity refers to the regions of the brain that any given neuron has axonal projections to. Based off of that, I was able to clean the data. It was all in MATLAB. It was kind of difficult to parse through, but we were able to label everything. So we were able to have a total of 4 data sets. The first two data sets were audio. The last 2 data sets were motor. And then for each of those categories, respectively, there's one data set that had just genetic information, the gene expression for various neurons that were found. And then there was a smaller data set that found not only the gene expression of various neurons, but also the neuronal connectivity type that each of those neurons had. So for each of those neurons, we had both sets of data of the genes that were being expressed, at least the ones that were measured, and then also the connectivity that it had, the axonal projections to various parts of the brain. So based off of these data sets, we were able to clean it and distill it down even more, so that we found that there were a total of 1,300 or so neurons for the audio cortex that had 20 genes total, and then 12 different types of axonal projections. And what we did, we calculated just the maximum axonal projection per neuron, which gives pretty much the primary direction that each neuron is trying to connect to. And that made it so that we were able to create a classification problem. As you can see, the motor data set was slightly larger with almost 2,000 different types of neurons, with 23 different types of genes and 36 connectivity types. As you can see, however, given the amount of categories that we had, this actually ended up being a problem that didn't need very, very complicated neural network types like convolutional neural networks. So with a multi-layer perceptron, we're able to get the best possible results. And what we found is that accuracy topped out at around 50% for the audio neurons and around 60% for the motor neurons. So in any case, even though this is fairly low, it still proves that there's a lot of correlates in this new emerging field that is linking gene expression to the connectome research in a lot of neuroscience. And this it shows a path forward for a sort of a data science driven approach to finding correlates between these things. So thank you very much.